Okay, a sample of 100 babies were born at SLU Hospital and had a mean weight of 3,072 grams with a standard deviation of 748 grams. The first thing I want us to do is use a single value to estimate the mean weight of a newborn baby. Well, because we only have one value here, right? This is our mean that we're given. We're going to use 3,072 as our estimate grams. Next, I need to find the margin of error and round to 2 decimal places. Remember, error is 1.96 times our standard deviation over the square root of our population size. So I have 1.96 times 748 over the square root of 100, and that's going to give me 146.6 grams. Next, I'm going to find the 95% confidence interval. Let's go ahead and do that up here. Remember, my confidence interval is my mean minus my error, and my mean is plus my error. So I'm going to take 3,072 minus 146.6, and I'm going to take 3,072 plus 146.6, and I get a 95% confidence interval of 2,925.4 is less than our population mean, which is less than 3,218.6. So what I've done here is I've constructed a 95% confidence interval. And what does that mean? That means I am 95% confident that the true population mean lies in between the values of 2,925.4 and 3,218.6. Okay? Last thing I want us to do is if I wanted a margin of error size, so if I wanted this to be my error size, what sample would I need? Now there's 2 equations, one for proportions to calculate the sample size and one for means. We are looking at means, and the equation for that is going to be n equals 1.96 times s. That s should give it away, right? Populations, proportions don't have standard deviations. Over our error, clean that up, over our error squared. So I have 1.96 times 748 over 100 squared. That gives me 2.14, no point there, got a little hasty. That gives me 214.94. Now, you cannot have 0.94 babies, right? So we're going to want to round up. When it comes to sample sizes, we always want to round up to, in this case, it's going to be 215. So we'd have to, in order to have a margin of error of 100, we would need to round up to 215 babies, right? The smaller our error gets, the bigger our sample size needs to be. Okay, let's take a look at problem 9. This is from our section on linear regression. So what I want you to do is estimate the R value. So let's take a look at our graph. Okay, my slope is negative, so I know I'm going to have a negative R value. It's going to be less than 1 because it's not a perfect relation. But my points are all over the place, right? They're everywhere. They aren't even super close to my line of best fit, this guy right here. So I know that I have a weak correlation. So why didn't I say 0.2? Is this correlation weak or strong? It's weak. Why is my correlation weak? Because my points are everywhere, right? If I wanted to have a strong correlation, let me illustrate that. If I wanted a strong correlation in the blue right here, my points would be really close to my line. And these little black dots, they're far away. I got something all the way up here. That's an outlier, okay? Next, I want to know what R squared tells us. Not what R squared is, which would be negative 0.2 squared, right? But what R squared tells us is what proportion of variation is accounted for by the best fit line. I'm going to say that again. R-squared tells us what proportion of variation is the key word I want to see, is accounted for by our best fit